Picture this. You are drifting in a universe where distance becomes time and time becomes history. The faint blur in the constellation of Andromeda is not a star or a cloud of mist. It is an entire galaxy, home to more than 1 trillion suns. The light you see from it tonight began its journey 2.5 million years ago, long before humanity carved tools from stone or painted on cave walls. You are not looking at Andromeda as it is, but at Andromeda as it was. Imagine drifting upward through the darkness, past our solar system, past the glowing spiral of the Milky Way, into the silent void between galaxies. Ahead of you, Andromeda unfurls like a continent of stars, larger than our own, its halo extending like a ghostly crown of invisible matter. What secrets hide within a galaxy so vast it can pull worlds toward it across millions of light years? If journeys like this help you sleep or see the universe differently, like and subscribe. Tell me where you're listening from tonight. Let's begin. For centuries, Andromeda was nothing more than a smudge of haze in the darkness. We catalogued it as a nebula, just another cloud inside our own galaxy. Only in the early 20th century did Edwin Hubble shatter that illusion. The blur was an island universe of its own, impossibly distant and unimaginably large. With that revelation, humanity learned that our Milky Way was not the universe, but only one city in a cosmic metropolis. The mistake was not born of ignorance, it was born of perspective. Ancient astronomers had no reason to suspect that faint wisps in the night sky were entire galaxies, each containing billions of stars. When they gazed upward, they looked through the thick fog of our own spiral arms. The stars of the Milky Way formed a bright river across the night, and anything dimmer was assumed to be part of it. The universe was a dome above Earth, mysterious yet contained. For most of humanity's history, that assumption felt obvious. It was even comforting. The world was vast, but not incomprehensible. Telescopes transformed that certainty into doubt. When Galileo first turned a lens toward the heavens, the sky fractured. The smooth bands of the Milky Way broke into countless points of light. Every star was a sun. Every sun could be a home. The cosmos was no longer a painted ceiling, but a landscape stretching beyond the imagination. Yet even then, the hazy smudge of Andromeda remained unsolved. Early astronomers called it a spiral nebula, believing it to be a structure floating inside our galactic neighborhood. Beautiful, but local. In 1923, Hubble forced the universe to confess. Using a powerful telescope at Mount Wilson Observatory, he studied faint stars within Andromeda and identified a special kind of stellar pulse. These stars brighten and dim at precise intervals, allowing astronomers to calculate their distance. The measurement Hubble derived was staggering. The Andromeda Nebula was not a nearby cloud. It was more than 2 million light-years away. A galaxy. A separate universe. A neighbor so large that its spiral arms would dwarf the Milky Way. The discovery landed like a cosmic earthquake. Every textbook, every star chart, every scientific assumption about the scale of the universe was suddenly wrong. Humanity had thought its galaxy was everything, the grand stage of existence. In an instant, the stage became a single room in a mansion whose size we could barely measure. The universe was no longer a local playground. It was a continent of galaxies stretching into darkness. The implications rippled outward. If Andromeda was a galaxy, then all the other spiral nebulae were galaxies too. Virgo, Triangulum, Sombrero. Structures so vast that Earth, the Sun, and even the Milky Way became footnotes. The cosmos was not populated by a few scattered stars. It was filled with islands of light separated by oceans of emptiness. The word galaxy lost its singularity and became plural. The scale of everything multiplied, then multiplied again. Suddenly, 2 million light-years was just our neighborhood. Humanity had misread the sky not because it was foolish, but because our senses are built for survival, not for cosmic comprehension. A faint blur to the naked eye could have contained 1 billion worlds and still seemed unimportant. Our ancestors stared at Andromeda every night and saw only a stain. They were standing in Times Square and mistook Manhattan for the entire planet. And that is how the universe introduces itself, not with fireworks, but with illusions. It hides its largest truths behind faint signals, trusting that someone, someday, will learn to measure their meaning. Hubble's discovery was the moment our species stepped outside its own walls. We stopped thinking of the Milky Way as the universe and began to understand it as a single house on an endless, starlit street. Most people who look up at Andromeda tonight still see what their ancestors saw: a blur, a smear of light between constellations. Yet within that blur lives a trillion suns, hundreds of billions of planets, and a cosmic history older than Earth itself. Sometimes the greatest mistake humanity makes is assuming the universe is small simply because it appears that way. And sometimes all it takes to correct that mistake is one pair of eyes, a telescope, and the courage to believe that the smudge in the sky might be everything we didn't know. Andromeda is not modest. It is a barred spiral more than 220,000 light-years across, hosting well over 1 trillion suns. Where we see soft light in telescopes, every pixel hides stellar nurseries, dying giants, and planetary systems no one will ever see. If the Milky Way is a sprawling city, Andromeda is an entire continent. Across its disk, stars are arranged in grand spirals that sweep outward like the arms of a vast storm. In the ultraviolet, newborn clusters shine in bright streaks, tracing lanes of gas that collapse under gravity into stellar nurseries. In the infrared, dust glows faintly, wrapping new stars in cocoons that human eyes cannot detect. This is not a passive sky ornament. It is a galaxy in motion, an engine humming with star formation, death, and rebirth that has continued for billions of years. At the galaxy's heart, a bulge of old stars sits like an ancient capital. Many of these suns lived and died before Earth formed. Their light is soft and red, a subtle glow that leaks through the galactic core like embers. Deeper still, past the crowds of stars and gas, Andromeda shelters a supermassive black hole, tens of millions of solar masses compressed into a region smaller than a solar system. The stars orbiting it form a tight nest, circling at dizzying speeds, some completing an orbit in just a few years. Our Sun, by contrast, takes more than 200 million years to circle the Milky Way. Farther out, the spiral arms hold a different population: younger, larger, hotter stars. Blue giants burn with an intensity that makes the sun seem quiet and restrained. They live short, spectacular lives, often ending in supernovae that seed the galaxy with heavy elements: iron for planets, carbon for life, gold for civilizations that may one day rise and fall. Andromeda is not simply a galaxy, it is a foundry, smelting matter into new forms again and again. Between the arms, darkness dominates. But even the dark is not empty. There, drifting between star clusters, lie rogue suns, exiles from ancient mergers. Some are the remnants of smaller galaxies that Andromeda consumed. Others are wanderers, tugged away by gravitational tides as the galaxy reshaped itself. These stars are silent witnesses of cosmic violence, drifting in isolation through a region so vast it humbles imagination. In the outer disk, faint globular clusters orbit like drifting lanterns. Each one holds hundreds of thousands of stars packed together into a single compact sphere. They are ancient, 13 billion years old in some cases. Older than Earth, older than the Sun, older than the Milky Way's spiral arms. They are the fossils of galactic formation, relics that survived every collision, every tidal fracture, and every gravitational upheaval Andromeda has endured. If you could count Andromeda's stars one per second, you would spend more than 30,000 years before reaching the end. And the galaxy does not care. It continues spinning, producing new stars, consuming old ones, and quietly expanding into the dark. Every star, every speck of light in its arms, is a system of worlds. Some may be scorched deserts, others could be frozen gas giants. A few might host oceans, continents, and beings who once stared into their own skies and wondered what lies beyond. Human eyes see Andromeda as a blur. Telescopes reveal it as a disk. But reality is more complex. The galaxy is layered: a core of ancient light, spirals of young fire, and a halo of invisible matter reaching far beyond the visible stars. What you see is only the surface, like looking at the skyline of a megacity and imagining it ends where the lights stop. The difference is scale. This city is made of stars, and its borders stretch for hundreds of thousands of light years. The Milky Way is impressive. It is vast. It is home. But compared to Andromeda, it is not the capital of the cosmos. It is a neighboring province. And somewhere across the intergalactic void, this colossus of stars continues to rotate, silently growing, waiting for the day when its gravity changes the fate of everything around it. There is no sharp boundary where a galaxy ends. Andromeda dissolves into faint light and gravitational influence. Scientists trace its true extent by star counts, X-ray emissions, globular clusters, hydrogen maps, and the motion of satellite galaxies. Each technique reveals a different rim, until they overlap to show the real structure. A galaxy far larger than what human eyes perceive. Astronomers call this challenge the problem of the galactic edge. Unlike a planet or a moon, a galaxy has no clean surface. Its brightness fades gradually, thinning into the dark, with no clear border to tell us where Andromeda stops. What looks like emptiness may be ancient stars drifting in the halo. What appears to be blackness may be gas too diffuse to glow. The galaxy is not a coin, it is an ecosystem, its outer reaches whispering rather than shouting. The simplest method is light itself. Point a telescope at Andromeda's outskirts and record the intensity of starlight as distance increases. At first, the spiral arms appear clear and structured, but the glow becomes faint, then barely measurable. Astronomers follow that diminishing trail until the light sinks below detection. That is the photometric edge, not a wall, but a vanishing point. On paper, it seems precise. In reality, the universe is noisy. Dust clouds dim stars, interstellar gas absorbs light, and cosmic background radiation creeps in like static, blurring the line between galaxy and void. So astronomers look for different markers. Globular clusters, compact balls of tens of thousands of stars, act like breadcrumbs. They orbit far from the galactic center, tracing invisible gravitational pathways. If you map enough of them, you eventually see how far Andromeda's influence extends. Some clusters wander more than 220,000 light-years from the core. These are not outliers, they are signposts. Gas reveals another layer. Radio telescopes listen for the 21-centimeter emissions of neutral hydrogen, whispers that pierce dust and darkness. Hydrogen traces where cold clouds linger, stretching far beyond the bright disk. A casual observer might believe Andromeda ends at the limits of optical images, but in radio, the galaxy keeps going, its tendrils reaching deeper into the void. Then there is hot gas, invisible to our eyes but radiant in X-ray wavelengths. Space telescopes reveal a glowing halo around Andromeda, millions of degrees hot, simmering within its gravity. That halo does not form randomly. It is contained, trapped by the galaxy's mass, marking an outer region of influence. The deeper you look into X-ray emissions, the larger Andromeda becomes. Gravity itself offers the most compelling evidence. Every star, globular cluster, and dwarf galaxy caught in Andromeda's pull is a messenger of mass we cannot see. Astronomers study their motion, charting the speeds at which they orbit the core. If the galaxy were limited to its visible stars, the outer regions should drift away, unable to remain bound. But they don't. They remain captured, proof that an unseen force is at work. This is the signature of dark matter. A massive halo surrounds Andromeda, heavier than every star and gas cloud combined. It bends orbits, traps satellites, and shapes the galaxy's true boundary. Without it, Andromeda would unravel like threads from a loose cloth. With it, the galaxy stretches outward to a scale almost impossible to visualize, its gravitational footprint spanning hundreds of thousands of light-years. The final measurement is the motion of others. Andromeda does not drift alone. Dwarf galaxies orbit it like moons around a planet. Their trajectories reveal where the host's gravitational field dominates, just as the shape of a tide reveals the presence of a hidden moon. Some dwarfs move along narrow arcs. Others travel in looping paths. Each motion is a sentence, and together they write the biography of Andromeda's invisible edge. No single technique tells the truth. Only when all are layered, light, gas, clusters, temperature, motion, does the galaxy reveal its real shape. It is not the postcard spiral we see in photographs. It is a sprawling gravitational empire, its influence stretching far beyond its stars, reaching into territory where even light cannot speak clearly. To measure Andromeda is to measure absence as much as presence. Its edge is not drawn by what we see, but by what still answers to its pull. The visible stars are only the paint on Andromeda's canvas. Beneath them lies a massive halo of dark matter, an invisible sphere hundreds of thousands of light-years wide. It does not glow, it does not radiate, but it holds more mass than every star, cluster, and nebula in the galaxy. Without it, Andromeda would fall apart. Dark matter has no color, no heat, no texture. It does not scatter light or interact with photons. It slips through gas clouds, planets, human instruments, and even through your body without leaving a trace. And yet, it is there, undeniable, measurable not by what it is, but by what it does. Like wind bending the branches of a tree, it reveals itself only through the movement of the galaxy it holds together. Andromeda spins too quickly for its luminous material to remain bound. Its outer stars whirl around the core as if in defiance of gravity. If starlight were the whole story, they would be flung into space like sparks from a grinding wheel. But they do not leave. Something heavier, colder, and larger surrounds them. Astronomers call it a halo, but the term is misleading. We imagine halos as elegant rings. Dark matter is not a ring. It is a vast, spherical cocoon, extending far beyond the bright disk, beyond the spiral arms, beyond the globular clusters, beyond the faintest streams of shredded satellites. If Andromeda's glittering stars are the skin, the halo is its skeleton, the internal framework that shapes everything else. To measure it, scientists analyze rotational curves, graphs of orbital velocity plotted against distance from the galaxy's center. In a universe without dark matter, the curve should drop off like a roller coaster cresting its peak. Instead, Andromeda's rotation remains stubbornly flat. Even far from the luminous disk, stars orbit at almost the same speed as those near the core. This is not a subtle deviation. It is a statement. Something enormous and invisible contributes the bulk of the mass. The halo is not uniform. It is lumpy, textured, scarred from the galaxies Andromeda has devoured. When smaller galaxies pass too close, tidal forces tear them apart. Their stars scatter into long streams, like silk threads pulled from a fabric. These streams trace the contours of the dark matter halo, winding around it, twisted by it, revealing its shape the way dust reveals wind. You do not see the monster directly. You see the marks it leaves behind. Andromeda's satellites orbit inside this invisible arena. Their motions are governed less by the stars they see than by the dark mass they cannot. Some dwarf galaxies move slowly, hugging the halo's edge. Others race along curved trajectories as if sliding down an unseen slope. The halo dictates their paths like a gravitational conductor. Scientists model these orbits and find consistency only when they include a halo roughly 1 to 2 million light-years in diameter. That means Andromeda's empire stretches across a distance so vast it overlaps with the halo of the Milky Way. Where the two halos touch, gravity is not silent. Forces whisper across the void, bending trajectories in ways we only now begin to measure. Most people imagine galaxies as isolated spirals, drifting alone. That picture is obsolete. Even now, this invisible skeleton, is reaching toward ours. Not violently, not dramatically, but with a slow inevitability only cosmic time can appreciate. Dark matter raises deeper questions. What is it? Are we looking at undiscovered particles, folds of space-time, remnants from the early universe? Theories multiply like branches, but no experiment has yet grasped the root. We know more about the surface of Andromeda's stars than we do about the substance that outweighs them tenfold. And yet, the halo's existence is undeniable. Without it, Andromeda would unravel. With it, the galaxy stands as a colossus, stable, ancient, and powerful. You see the stars, the spirals, and the brilliant core. But the true Andromeda, the vast structure that shapes its past and future, is something you will never see. You can only feel its gravity tugging across the universe, holding the galaxy together in its invisible embrace. Unlike the smooth spirals of textbooks, Andromeda's structure is punctuated by a colossal ring of star formation encircling its core. Cold gas compresses into knots, collapses, ignites, and creates new suns by the millions. That ring keeps Andromeda alive, recycling cosmic debris into fresh stars like a furnace that never truly cools. Astronomers call this feature the 10 kiloparsec ring, but the name barely captures its scale. Stretching tens of thousands of light-years across, it is a stellar nursery on a galactic level, an orbital belt where gravity, gas, and time cooperate to forge newborn suns. When telescopes observe Andromeda in infrared or ultraviolet wavelengths, this structure flares into view like a crown. In visible light, it is subtle. In deeper wavelengths, it burns brighter than the spiral arms themselves, pulsing with the energy of continuous creation. Inside this ring, cold clouds of hydrogen drift like cosmic fog. They are silent until gravity finds them. Once mass accumulates, the clouds collapse inward, heating and compressing until their cores ignite nuclear fusion. A star is born when hydrogen atoms fuse, releasing energy that pushes outward against the same gravity trying to crush it. This balance, simple, elegant, violent, is the engine of the universe. Andromeda's ring holds thousands of such engines in various stages of ignition, each a sun that will one day sculpt its own system of worlds. The ring is not a random feature. It is a wound reshaped into beauty. Many astronomers believe it formed after a collision with a smaller galaxy, perhaps Andromeda's companion M32. When galaxies interact, tidal forces ripple through their disks. Gas flows inward, then outward again, creating waves like ripples in a pond. The densest parts compress into star-forming belts. Over millions of years, those ripples become rings. In Andromeda, that ripple became a permanent scar, a place where cosmic material is continually forced together. Not all stars born here are gentle. Some are O-type blue giants, dozens of times hotter than the sun and hundreds of thousands of times brighter. They blaze with fierce ultraviolet radiation, stripping surrounding gas and sculpting cavities into the nebulae that birthed them. But they pay for their brilliance with a shortened life. Many will die within a few million years, exploding as supernovae that hurl heavier elements outward into space. Iron, silicon, calcium, materials that make soil, stone, blood, bone. In the ring, stars do not simply form. They create the ingredients for future planets. The ring is also a laboratory of time. Different regions are at different stages of stellar evolution. Some are dense knotted clouds on the brink of collapse. Others are filled with clusters of bright newborn stars. Other patches look ragged, as if scraped clean by radiation and shockwaves. It is the galactic equivalent of watching forests grow, burn, and regrow over thousands of seasons, each cycle slightly different from the last. Andromeda's spiral arms extend beyond the ring, but there the pace of creation slows. Gas is thinner, turbulence weaker, and the gravitational compressions less intense. The arms host older stars migrating outward, a quieter population compared to the blazing youth of the ring. If the galaxy were a living thing, the ring would be its heartbeat, steady, powerful, unending. From Earth, we inherit only whispers of this process. To our eyes, Andromeda is a pale smear in the sky. Through a small telescope, it becomes a disk. But only space observatories, Spitzer, Hubble, Webb, reveal the true texture of its ring. In infrared images, glowing knots and filaments light up like embers in charcoal. In ultraviolet, the youngest stars appear as bright shocks in the darkness, like sparks flung from a cosmic forge. The Milky Way has its own regions of star formation: Orion, Carina, Cygnus, but nothing like Andromeda's circular belt. Our galaxy is less dramatic, its nurseries scattered along spiral arms like small pockets of growth. Andromeda centralized the process. It built a ring and used it as a crucible, merging ancient gas with fresh material stripped from smaller galaxies. In this furnace, the past becomes the future, matter recycled into light. That is the secret of the Ring of Fire. It is not merely a location, it is an ongoing act of creation, a reminder that galaxies are never static. They breathe, they consume, they burn, and in the depths of Andromeda, the stars continue to ignite, each one another flame in a circle that has been glowing for millions of years and will likely continue long after our own sun has faded. Deep in the galaxy's center sits a supermassive black hole tens of millions of times heavier than the sun. Its gravity sculpts the orbits of surrounding stars. Occasionally, a wayward gas cloud drifts too close. The hole consumes it, heating its surroundings into X-ray storms that ripple through the core like distant artillery. A black hole is not a hole in the sense our language suggests. It is a region where mass is so densely packed that even light cannot escape. Andromeda's central black hole, known as M31, weighs more than 100 million suns. That immense mass does not announce itself with a glow. It announces itself with control. Every star in the central bulge moves in response to it, tracing invisible patterns across the core as though tethered to a silent conductor. To the naked eye, Andromeda's core looks calm, a soft cluster of ancient stars, their light yellowed by age and distance. But in less gentle wavelengths, the calm evaporates. Radio and X-ray telescopes reveal heated gas spiraling inward, forming a thin disk around the black hole. Friction tears matter apart, accelerating it until it glows hotter than the surface of most stars. That disk is where matter dies, atom by atom, and where the black hole feeds. Unlike stars, a black hole does not need to touch what it consumes. Gravity stretches incoming gas clouds until they fray like strands of silk. The gas falls inward, forming arcs and ribbons that spiral toward oblivion. Many never reach the event horizon, the point of no return. They are torn apart earlier, scattering radiation into space. When this happens, telescopes capture sudden bursts of X-rays, brief flares that fade as silently as they appeared. Orbiting this chaos is a dense cluster of stars, packed so tightly that distances we consider enormous become negligible. Some complete an orbit of the core in only a few years. For comparison, our Sun takes more than 200 million years to circle the Milky Way. Near Andromeda's heart, time itself seems compressed. The gravitational pull is so strong that a star cannot wander, only obey. The core holds another surprise, a double nucleus. When astronomers observed it closely, they found not one central bright knot, but two. For a time, this seemed like evidence of a second black hole. Later, simulations revealed a subtler truth. The stars orbiting the central region do not form a perfect sphere. They move along elongated paths, clustering at 2 points in their orbit. We see these concentrations as separate centers of light, when in reality they are just the geometry of motion in a tilted gravitational well. The black hole is not constantly active. Most of the time, it waits. There is less gas near Andromeda's center than people imagine. The violent flares we detect are not the galaxy's heartbeat, they are accidents. A drifting cloud, a disrupted star, a fragment of tidal debris from an ancient merger. When fuel arrives, the monster wakes. When the meal is gone, it sleeps again. Despite the drama of its feeding, the black hole is a stabilizer. Without its central gravity, stars would drift outward, the bulge would unravel, and the entire galaxy would lose coherence. Supermassive black holes do not sit at the centers of galaxies by coincidence. They anchor them. They shape growth, moderate turbulence, and convert destructive energy into heat that radiates through space. We cannot see M31 directly. We witness its influence. We measure the speeds of nearby stars and trace their orbits backward. We watch sudden X-ray flashes as matter falls inward. Every observation points to the same conclusion. At the heart of Andromeda lies a force we can describe with mathematics, but never fully comprehend. It is both the galaxy's predator and its foundation, a creature of gravity that keeps the Colossus intact. Andromeda did not grow politely. It devoured its neighbors. Over billions of years, it shredded dwarf galaxies and absorbed their stars. Their remains hang today as faint stellar streams and arcs in its halo, long, ghostly trails suspended in orbits like scars from ancient conquests. The halo of Andromeda is not empty space. It is an archive of broken worlds. Each faint ribbon of starlight traces a smaller galaxy that once drifted too close. Gravity stretched it, stripped its stars, and folded them into long, curling streams. These stellar rivers wrap around Andromeda like the debris of forgotten battles. They tell astronomers where galaxies were torn apart and when. Some are thousands of light years long, their stars scattered like ashes. To the naked eye, it is nothing. To deep imaging, it is carnage frozen in slow motion. The largest of these victims left behind recognizable remnants. Once, they were dwarf galaxies, compact systems with billions of stars, dark matter, and gas. They orbited Andromeda for hundreds of millions of years, unaware that every pass eroded their structure. Over time, tidal forces pulled them apart. Their cores grew dim, their stars drifted outward, leaving only loose knots of survivors. These remnants still exist today. Fragments like the dwarf galaxy M32, tightly bound and stripped of much of its outer material, and M110, an elongated husk that may be living its final chapter. When astronomers first mapped these streams, they assumed they were isolated features. The more telescopes looked, the more they found. Arcs upon arcs, loops upon loops. It became clear that this was not a single meal, but a long history of consumption. Andromeda has eaten dozens of galaxies. It is not merely large. It is a product of endless assimilation, each collision adding to its mass, like layers of sediment forming a mountain. Some streams show relatively fresh scars. Their stars share similar ages and velocities, suggesting a galaxy was consumed only a few 100 million years ago, recent in cosmic terms. Others are ancient. Their stars are older, their orbits smoother, their trails faint and diffused. Time has blurred them, the way ocean waves erase footprints in the sand. In these fading arcs lie galaxies that died when dinosaurs still walked the Earth. Their final traces stretch so thin, they barely register in telescope images. This cannibalism is not cruelty, it is physics. Small galaxies lack the momentum to resist the gravitational well of giants. They fall inward, spiral around, and inevitably disintegrate. Even our own Milky Way practices this same hunger. It is devouring the Sagittarius dwarf galaxy right now. In cosmic ecosystems, survival belongs to mass. The large consume the weak, and those that endure become larger still. But Andromeda is exceptional in one way. Its appetite has been more intense than ours. Observational surveys suggest it absorbed a massive galaxy roughly 2 billion years ago, a collision so significant that it may have reshaped its halo and influenced its star-forming ring. The event injected stars into new orbits, thickened the central bulge, and may have ignited bursts of starbirth. Even after digestion, the evidence remains encoded in the motions of stars. They move not like native inhabitants, but like refugees, circling the galaxy in wide, looping paths. The halo is full of such ghosts. Some move in tight braids, others in arcs that wrap Andromeda like bandages. Each one is a record of violence. When scientists model these paths backwards in time, the torn galaxies reassemble like shattered pottery. The orbits converge, forming compact shapes, former homes. For a moment, the dead systems live again, if only in simulation. Look closely, and Andromeda's halo becomes a graveyard. Every faint structure is a eulogy, every star a survivor. These remnants remind us that galaxies do not grow peacefully. They harvest, they absorb. They rewrite the identities of those unlucky enough to drift into their grasp. And at the center of this great predator stands a spiral of light, pretending to be serene, even as the bones of the galaxies it consumed drift quietly in the darkness around it. Beyond Andromeda's disk swarm dozens of companions, bright dwarfs like M32 and M110, but also dozens of barely visible satellites. They orbit not because they choose to, but because gravity leaves them no other option. Many exist only until Andromeda tears them apart. These satellites drift through the outskirts like embers flickering around a bonfire. Each is a galaxy in its own right, some containing a few billion stars, others only a few million. They are fragile worlds with shallow gravitational wells, their mass too small to resist the pull of Andromeda's halo. Their orbits trace huge arcs through space, crossing regions where tidal forces stretch them thin. Some survive for billions of years. Others are already in the process of being dismantled. Their stars shed like dust from a comet's tail. The most famous of these companions is M32, a compact elliptical galaxy so heavily stripped that it resembles a polished core. Long ago, it may have been much larger, perhaps a spiral like the Milky Way or triangulum, but Andromeda has carved it down to the bone. Its arms are gone, its outer layers absorbed. What remains is a dense, glowing sphere that orbits close to Andromeda's center, like a moon that has been smoothed by repeated impacts. Nearby drifts M110, softer in shape and scarred by age. Its elongated form hints at past distortions. It may once have been round, but the gravitational tides of Andromeda have tugged it into a stretched, asymmetrical frame. Inside, its stars are older, quieter, less prone to forming new suns. It lingers in a delicate balance, too close to break away, too intact to be fully consumed, at least for now. But M32 and M110 are only the celebrities. Surrounding them are more than 50 smaller dwarfs, many so faint they were discovered only in the last decade, through deep surveys and long exposures. These galaxies are so dim that a billion stars might appear as a smear of background noise. Their gas reserves are nearly non-existent. Many are quenched, meaning they have stopped forming new stars entirely. They are dry husks, wandering through the halo like skeletal caravans. Their orbits tell stories that light cannot. Some travel in broad, looping motions. Others circle tightly, like satellites caught in deep gravity wells. A few don't orbit at all, at least not yet. They are newcomers, recently captured by Andromeda's halo, still settling into paths that will eventually decide their fate. These galaxies behave like birds caught in a thermal vortex, spiraling, drifting, and slowly losing energy until they fall inward. The strangest feature of Andromeda's outer kingdom is its disk-like plane of satellites, a flattened structure where many dwarf galaxies line up in a common orientation. For years, astronomers assumed satellite systems were scattered randomly, like meteors around a planet. Andromeda defies that expectation. A significant fraction of its dwarfs orbit in a coordinated sheet, as if remnants of a single long-ago collision were still following the echoes of that event. The pattern is so specific that it challenges models of galaxy formation and dark matter distribution. This kingdom is not quiet. When a dwarf galaxy passes too close to Andromeda, its stars peel away. Some form elongated streams that wrap the halo like ribbons. Others fall inward and merge with the disk. Every interaction feeds Andromeda, adding mass, deepening its gravitational influence. The dwarfs that cling to the outskirts are not spectators. They are resources waiting to be claimed. Even the independence they once had is now an illusion. Their stars orbit Andromeda more than they orbit their own centers. Their motion is dictated by the gravitational skeleton beneath the visible galaxy, the dark matter halo. To them, Andromeda is not a neighbor. It is the sky. The invisible force beneath reality has already chosen their destiny. In the vast, empty space beyond the galaxy's bright arms, these satellites drift, fade, and fall. Some will be spared by distance, settling into long-term orbits like distant moons. Others will be stripped away until nothing remains but their names in the memory of astronomers. This is the outer kingdom of Andromeda, beautiful, fragile, and ruled by gravity alone. In the deep outskirts, astronomers find fossilized rivers of stars. They are not random. They are the shredded bones of the galaxies, Andromeda consumed. Their motion reveals the galaxy's hidden mass, just as shattered bones show how a predator hunts. These pale streamers of starlight, some stretching tens of thousands of light years, are fragile relics of cosmic violence. They drift in Andromeda's outskirts like ribbons torn from ancient banners, curled around the galaxy in wide, looping arcs. You cannot see them with your eyes, or even ordinary telescopes. They emerge only in deep exposures, where astronomers stack images and sift through the faintest signals of light. What appears to be empty space suddenly fills with the ghostly trails of long-dead galaxies. Each of these streams is a story. They once belonged to dwarf galaxies, rich with stars and dark matter. Some were compact and spherical, others spiral miniatures. They wandered too near Andromeda's gravity and were captured. They orbited for eons like moths circling a flame, until tidal forces ripped them apart. Their cores disintegrated, their stars stretched into elegant chains that trace the history of their fall. If you map these stellar rivers, they draw patterns no two galaxies would produce by accident. They bend and weave, looping around the halo like silk threads pulled taut. Some wrap nearly a full revolution around Andromeda, their arcs so vast that they take hundreds of millions of years to complete a single orbit. Others appear as disjointed segments, where the remains of a galaxy have already been partially swallowed, like vertebrae scattered along a trail. To an astrophysicist, these skeletons are priceless. They tell us where Andromeda's gravity is strongest and how far its influence reaches. Stars in the streams move together, like schools of fish. Their velocities, directions, and dispersions reveal the invisible architecture of the dark matter halo. This is how astronomers reconstruct the galaxy's skeleton, not through brightness, but through motion. The largest stream is known as the giant stellar stream, a tidal river that arcs beneath Andromeda's disk. It is the wreckage of a once substantial galaxy, torn apart perhaps 2 billion years ago. Its stars are older than many of those in Andromeda's spiral arms, and they move through space like mourners walking through the ruins of their home. In simulations, researchers rewind the stream, star by star, until the fragments merge into a singular shape. A galaxy reappears. Then the simulation lets gravity run forward, and the galaxy unravels again, its stars smeared into luminous trails that match what telescopes see today. This forensic approach turns Andromeda into a crime scene. Every stream is evidence. Every remnant is a witness. The halo becomes a gallery of confessions. Records of mergers, disruptions, and slow dismemberments stretching across a cosmic timeline. Nothing about these structures is accidental. Some streams glow faintly in the infrared. Others appear only when astronomers examine the composition of stars, searching for unusual metallicities, chemical signatures that mark them as outsiders. They do not share Andromeda's stellar DNA. They carry the imprint of their birth galaxy, different levels of iron, magnesium, or carbon. They are interlopers, adopted only after their homes were destroyed. Even more subtle remnants lurk in the halo, shell structures and faint arcs that resemble the ripples of a stone dropped into water. These features form when a galaxy falls directly into Andromeda's center and rebounds outward, scattering stars into concentric curves. No spiral arms, no ordered structure, just scars layered like tree rings. The halo's pale skeletons have another lesson to offer. Andromeda's growth is not a single event, but a long ritual of accumulation. Large galaxies are not born massive. They are built from smaller bodies, each merger a brick in a structure billions of years in the making. What we see today, its stars, its mass, its gravitational dominance, is the consequence of endless consumption. In the silence of deep space, these stellar streams drift on, unchanged by human history. They are not dramatic. They are not loud. They are the bones of the fallen, glimmering faintly in the dark, reminding us that the beauty of Andromeda was forged through sacrifice. If you only counted visible mass, Andromeda should fling itself apart, its outer stars orbit too fast to remain bound. Yet they do. Their survival is proof of dark matter, a gravity engine that outweighs everything we can observe. The galaxy spins because something unseen is holding it together. Astronomers learned this by tracing how fast stars orbit the galactic center. Near the core, the speeds make sense. Gravity is strong, and stars behave like planets circling close to a massive sun. But as measurements extend outward, past the spiral arms, past the dust lanes, into the faint edges of the disk, something breaks. Instead of slowing down, the stars keep moving at nearly the same speed. The curve of orbital velocity, which should dip downward like a hill, refuses to fall. It stays flat, steady. The laws of physics do not bend for convenience. If only the luminous matter in Andromeda existed, stars, gas, clusters, nebulae, the galaxy would tear itself apart. The gravitational pull of the visible disk is simply too weak to bind the outskirts. Those stars would drift into intergalactic space like sparks cast from a spinning wheel. The fact that they don't means the galaxy contains mass we cannot see. That missing mass is dark matter. It does not emit light, reflect light, or absorb it. It passes through gas clouds without interacting, through stars without friction. We know it exists not because we detect it directly, but because gravity does. When scientists calculate how much mass is required to keep Andromeda intact, the number dwarfs every visible atom. The luminous galaxy we photograph is only the glowing core of a much larger structure. Imagine Andromeda as a lantern inside a glass sphere. The lantern, its stars and gas, provides the light. The sphere, its dark matter halo, provides the weight. The stars orbit inside this invisible enclosure, held in place by a form of gravity that does not radiate or burn. This revelation was not discovered in Andromeda alone. It emerged through the work of astronomers like Vera C. Rubin, who measured the rotation curves of many galaxies and found the same anomaly everywhere she looked. Outskirts too fast, inner regions too calm. The universe was speaking in a single voice. Andromeda simply helps us hear it clearly. Its halo extends far beyond the spiral arms, hundreds of thousands of light years into the void. Stars in this region orbit as though embedded in a massive, spherical web. Even dwarf galaxies caught in Andromeda's pull behave differently than they should. Their trajectories bend, their speeds accelerate, their orbits stabilize only when models include the unseen mass. Simulations confirm what observation suggests. When astronomers remove the halo from their calculations, Andromeda collapses. Only when the dark matter halo is restored do the models reproduce the galaxy as it truly exists, a disk of blazing stars bound by an invisible skeleton. We do not yet know what the halo is made of. Some theories propose undiscovered particles, others point to exotic physics. But the details do not change the conclusion. The halo exists, it shapes every orbit, and it is larger and heavier than everything we can photograph. When you look at Andromeda through a telescope, you see a delicate spiral of light. But what keeps that spiral intact is something darker, larger, and older than any sun. The galaxy rotates calmly, not because it should, but because it is held together by a force we cannot see, yet cannot deny. Every photon from Andromeda is a time capsule. It began its journey 2.5 million years ago, crossing empty space to reach your eyes. The galaxy you see tonight no longer exists in that form. New stars have ignited. Others have died. This is the strange truth about astronomy. We do not see things as they are. We see them as they were. Light has a speed, the fastest speed allowed in the universe, but it is not instantaneous. Even at 300,000 kilometers per second, crossing intergalactic space takes ages. When photons leave Andromeda, they begin a journey across a void so vast that entire species could evolve, flourish, and disappear before the light ever arrives here. Think of what 2.5 million years means in human terms. When the photons currently entering your eyes left Andromeda, Earth's early ancestors, Australopithecus, walked the savannas of Africa. Bodies smaller than modern humans, minds unshaped by language or writing or mathematics, lived under the same sky and saw the same blur. They could not know that the faint patch above them was a galaxy larger than their own. To them, it was simply one more light in the night. During those 2.5 million years, humanity learned to sharpen stones, to tame fire, to tell stories, to write, to build, and to reach into the heavens with machines of glass and metal. Empires formed and collapsed. The ancestors of modern cultures were born and forgotten, all while the photons continued their silent journey, crossing the gulf between galaxies without slowing, without deviation, carrying the memory of Andromeda as it once was. Somewhere in that time, stars in Andromeda exploded. Their light has not reached us yet. Somewhere else, a cluster of newborn stars flared into brilliance. We will not see them for millions of years. The galaxy is constantly evolving, but our knowledge lags behind. Every telescope image is an archaeological artifact, a snapshot of a distant past, not the living present. Even space telescopes cannot escape this delay. The James Webb Space Telescope, the Hubble, even future observatories with more sensitive instruments will still be bound by light's finite speed. They may show richer detail, deeper contrast, clearer structures, but they cannot break causality. The universe reveals itself only in echoes. Astronomers work with this delay the way historians work with ancient texts. They read the oldest light first, infrared remnants of the early universe, then younger light from spiral galaxies like Andromeda, and finally the newest whispers from nearby stars. They analyze the past to infer the present. A galaxy's structure, its motion, its star formation rates, its collisions, these are pieced together from signals delayed by time. Sometimes, the delay works in our favor. It gives us a timeline of cosmic evolution. We see galaxies in different eras, some still forming, some mature, some dying. The night sky becomes a museum of epochs, each object exhibiting a different chapter of the universe's story. Andromeda, bright and close, is simply the nearby exhibit, one we view from 2.5 million years ago, long before the Milky Way and Andromeda felt each other's gravity as strongly as they do today. And sometimes, the delay forces humility. We do not know what Andromeda is right now. Perhaps a supernova has torn open one of its spiral arms. Perhaps a dwarf galaxy has fallen into it, fueling a burst of star formation. Perhaps nothing remarkable has happened at all. Our vision of Andromeda is not the galaxy's present. It is its fossil. Light is a courier. It does not update us. It delivers messages and then leaves us waiting for the next one. The space between galaxies is so vast that it traps time, stretching moments into aeons, forcing us to gaze backward into history even as we stand firmly in the present. Look up at Andromeda, and you are not seeing a distant neighbor. You are seeing a memory. The gulf between the two galaxies is not full of swirling gas. It is nothingness. Intergalactic space is so sparse that a cubic meter might hold a single stray atom. Yet the void is not neutral. Dark matter scaffolds stretch across it, pulling the galaxies like ships tethered by invisible ropes. If you could stand somewhere in the space between the Milky Way and Andromeda, you would not find a sea of stars. You would see nothing at all. No glow, no warmth, no air to breathe. The temperature would hover just above absolute zero, a place where even atoms move reluctantly. This region is called intergalactic space, and it is the closest thing to pure emptiness nature allows. The vacuum here is harsher than anything we can manufacture on Earth. A laboratory vacuum leaves trillions of atoms in every cubic centimeter. Intergalactic space leaves almost none. And yet, this emptiness governs the fate of every galaxy you can see. Gravity travels through it without needing matter to carry it. Andromeda and the Milky Way do not drift independently. They respond to the curvature of space-time carved by their mass. Their halos already touch in places, like two continents whose coastlines brush below the surface of an ocean. We think of galaxies as isolated islands, but they are more like mountain ranges rising from the same continental plate. The true structure of this emptiness is the cosmic web, a network of dark matter filaments that thread the universe. These filaments are invisible, but galaxies gather along them like dew on a spider's silk. Clusters form at intersections. Voids stretch between them. Andromeda and the Milky Way sit within the same gravitational basin, sliding inward along the same unseen slope. The void between them is not random. It is shaped by forces billions of years old. Occasionally, a star wanders here, a rogue ejected by a collision, or flung outward when a binary partner was swallowed by a supermassive black hole. These stars move silently, drifting for millions of years with no home galaxy to claim them. They do not light the void, they punctuate it. Astronomers sometimes detect them faintly, like distant flares in a sea of darkness, evidence of violence carried out long ago. For most of this space, there is no gas dense enough to form nebulae. Yet, ultra-thin clouds exist. Relics from ancient outflows, wisps of hydrogen or helium stretched across light years. They are so dilute that the air around a human body contains more molecules. We find them not by looking directly, but by noticing what they block. When light from a distant quasar passes through one of these clouds, it arrives scarred, carving shadows in the spectrum like fingerprints. From those shadows, astronomers map material too faint to see. Even the idea of motion becomes distorted here. The galaxies do not rush toward each other, they drift. Their approach is measured in tens of kilometers per second, a crawling pace on cosmic scales. If you could watch from the void itself, Andromeda would take longer than the geological age of Earth to cross a single degree of sky. And yet, nothing is static. Dark matter gently compresses space, guiding each galaxy along a path carved by mass rather than intention. Simulations show them circling each other's halos long before any stars pass close. The future of the local group is written in the shape of this emptiness. Not the galaxies themselves, but the silence between them. When you imagine the void, do not picture lifeless chaos. Picture potential. Where gas is thin, galaxies grow old. Where halos overlap, futures change. The gulf between the Milky Way and Andromeda is not a blank page. It is the boundary where two colossal stories meet, slowly, inevitably, across millions of light years. We are not isolated wanderers. The Milky Way, Andromeda, and more than 50 dwarfs form a small gravitational community. Most members are tiny and faint. A few are mid-sized, but only two are titans, shaping the fate of the others, us and the giant coming toward us. This community is called the local group, and it is our true cosmic home. It is not a tightly packed cluster, nor a swirling metropolis of galaxies like Virgo. It is quiet, modest, a few luminous residents surrounded by many dim ones, all sharing a common gravitational well. If the universe were a continent, the local group would be a sparsely populated valley between distant mountain ranges. At first glance, the local group seems simple: Milky Way, Andromeda, and Triangulum. Around these giants orbit dozens of lesser galaxies, small, faint systems with shallow gravitational wells. They drift like moths around lanterns, circling for billions of years without ever escaping. Some are luminous enough to see in amateur telescopes. Most are so diffuse that they barely qualify as galaxies at all. The two dominant powers, the Milky Way and Andromeda, control everything. Their halos extend hundreds of thousands of light years, and their influence overlaps in a region where dwarfs switch allegiance. The small Magellanic Cloud and the large Magellanic Cloud orbit the Milky Way for now, but their paths bend in subtle ways that hint at stolen momentum and ancient interactions. Andromeda has its own retinue, M32, M110, and a swarm of faint satellites stretched along its halo like beads on wire. The third major resident, Triangulum, sits between the roles of companion and understudy. It is a spiral galaxy, yet too small to pull others into its orbit. Some simulations suggest it may be bound to Andromeda, circling slowly like a child trailing an older sibling. Others show a temporary interaction, a brief gravitational conversation, before the galaxy drifts away. Its future, like ours, depends on how the Titans move. The dwarfs tell quieter stories. Many are ancient, older than the arms of the Milky Way. Their stars formed early in cosmic history, and when their gas was stripped away by tides or radiation, they became quiescent. 1 trillion cubic kilometers of space may contain a single star. Their dark matter dominates their structure, holding their few suns together like pebbles glued to the inside of a balloon. If you could hover above the local group, you would not see galaxies arranged neatly in a circle. You would see them scattered like islands on an ocean, separated by millions of light-years of void. They are bound together not because they are close, but because nothing is pushing them apart fast enough to escape. Beyond them lies the vast emptiness between groups, where galaxies drift freely toward larger gravitational basins. Our neighborhood sits inside the local sheet, a flattened region where nearby galaxies share similar motions. The sheet flows toward an even greater structure, Laniakea, the supercluster of which we are a tiny part. But within the local group, motion converges inward. The Milky Way and Andromeda dominate the gravitational landscape. Their trajectories bend toward each other, not dramatically, but inevitably, like two massive stones slowly rolling toward the same valley floor. If galaxies were sentient, the dwarfs would be anxious neighbors. Others are already dissolving, their stars stretched into streams that trace their final orbits. One day, some of these galaxies will be fully absorbed into the Milky Way, into Andromeda, or into the giant that eventually forms from both. In this quiet corner of the universe, the local group behaves like a family of unequal siblings. The elders shape destiny. The small ones endure, and in the center of it all, two giants drift slowly toward each other, carrying every other member along with them. For decades, astronomers believed the galaxies would collide in 4-5 billion years. Simulations showed spirals shredding, halos merging, and stars scattering like seeds in the wind. It became consensus. We drew animations, published models, and taught students that the cosmic crash was guaranteed. The logic was simple. Both galaxies are massive, gravitationally bound, and drifting toward each other. In astronomy, toward is usually destiny. Simulations run through the late 20th and early 21st centuries showed a straightforward conclusion. The Milky Way and Andromeda were two trains on a single track, approaching slowly but inevitably. That story fit the data and the scale of the cosmos, and it captured the imagination of everyone who studied it. Computer models projected an elegant catastrophe. As the galaxies neared, tidal forces would tear their spiral arms into long streamers of stars. Gas clouds would collide, igniting bursts of star formation that could illuminate the sky with millions of newborn suns. Over hundreds of millions of years, both galaxies would be reshaped, first into warped spirals, then into chaotic clouds of stellar debris. Eventually, the chaos would settle into a fat, elliptical galaxy. Its new name was already chosen, Milkomeda. This idea seeped into documentaries, textbooks, and even pop culture. We imagined the night sky transformed, Andromeda looming larger than the moon, a bright, expanding arc consuming constellations. It was cinematic, dramatic, and emotionally satisfying. The prophecy was that our galaxy would not survive in its current form. We would be swallowed, absorbed, our spiral arms erased like markings on a chalkboard. The beauty of the early models was their clarity. They operated on straightforward radial motion. Andromeda was moving toward us, therefore the galaxies would collide. The mathematics was clean. Astrophysicists had found a cosmic narrative with no ambiguity, and for nearly a century, no one meaningfully challenged it. But astronomy evolves the same way galaxies do, slowly, until a sudden disruption changes everything. The dream of inevitability began to wobble when astronomers gained better instruments. Early measurements saw the motion of Andromeda along one axis, its approach toward us. What they lacked was the sideways motion, the tangential velocity, how much Andromeda moves across the sky rather than directly inward. Without this, the collision timeline was an educated guess. Newer telescopes gave hints, but nothing definitive. Then Gaia arrived. Its precision was unlike anything before it, capable of tracking tiny motions of stars with extraordinary accuracy. Instead of seeing Andromeda as a single advancing object, Gaia let astronomers measure how stars within Andromeda were moving relative to us, revealing the galaxy's sideways drift. The result was not dramatic. It was subtle, just tens of kilometers per second in lateral motion. But in cosmic mechanics, subtlety is everything. A minuscule sideways movement across millions of light years becomes a massive deviation in trajectory. Suddenly, the prophecy fractured. What was once a guaranteed collision became something less certain, an encounter. Instead of two galaxies slamming together like cymbals, some models now show a shallow pass. The halos brush. The disks distort. The spirals do not crash head-on, but sweep past each other like dancers misaligned in their final step. The transformation still happens, but not as quickly. The interaction becomes a slow gravitational handshake rather than a flaming collision. For a moment, astronomers hesitated. This new picture was harder to dramatize. It did not produce dramatic supernova fireworks on schedule. It did not promise a neat end to galactic individuality. It offered instead what real science often delivers: nuance. The old prophecy of inevitability was not wrong, it was incomplete. The cosmos rarely tells its story in absolutes. Two galaxies approach each other with patience measured in billions of years, their fate written not in cinematic collision, but in the fine print of gravity, motion, and time. Then Gaia measured Andromeda's sideways drift, its motion across the sky, too subtle for earlier telescopes to detect. Those few micro-arc seconds per year rewrote the entire narrative. A tiny transverse velocity shifted a collision into an orbital dance. The future was no longer a straight line. For nearly a century, astronomers treated Andromeda as a projectile aimed directly at us. We could measure its radial velocity, the component of its motion along our line of sight, using the Doppler shift of its light. The galaxy was moving toward us at roughly 110 kilometers per second. That seemed clear, definitive, and terrifying. But radial motion is only half of a trajectory. It tells you how fast an object approaches or retreats, not whether it is sliding sideways. The missing piece was the proper motion: Andromeda's drift across the sky. Measuring that drift is astonishingly difficult. Andromeda is 2.5 million light-years away. The sideways motion we needed to detect would change its apparent position by less than a millionth of a degree per year. For decades, the instruments simply weren't precise enough. So astronomers assumed the lateral motion was negligible. They built simulations on that assumption, and the simulations agreed. Collision was inevitable. Then Gaia arrived. Gaia, a European Space Agency observatory, was designed to create the most precise map of the Milky Way ever attempted. It tracks the motion of individual stars with micro-arc-second accuracy, an angular resolution comparable to seeing the width of a human hair from thousands of kilometers away. It was not meant to solve the Andromeda question. But by measuring the motion of stars surrounding us, Gaia revealed something the older measurements missed: how Andromeda's halo is moving relative to ours. Instead of drifting straight toward us, Andromeda is gliding sideways. Only a small component of its velocity points inward. The rest is lateral, a sideways drift across the sky. That drift is slow, tens of kilometers per second, but stretched across millions of years and millions of light years. Two cars driving toward each other at highway speed will crash if their steering wheels are aligned. But if one car shifts its wheel just a degree to the side, it may miss entirely. On cosmic scales, Andromeda's sideways motion is that tiny steering correction. When this data entered new simulations, the future of the local group unfolded differently. In many models, the galaxies do not collide head-on. They approach, feel each other's gravity, and then sweep past each other. Instead of one catastrophic crash, they begin a long gravitational waltz, approaching, retreating, curving, and eventually spiraling inward over billions of years. Some simulations show multiple close encounters, each one a slow near miss. Spiral arms twist, gas compresses, stars are displaced, but the galaxies never fully merge. They become gravitational partners rather than immediate victims of destruction. The once certain doom evaporates into nuance. Not collision, but interaction. This sideways drift doesn't mean peace. Galaxies are not billiard balls bouncing harmlessly off one another. Their halos, their invisible cores of dark matter, interpenetrate even during flybys. That halo overlap can sap energy from their motions, slowly pulling them together. Over hundreds of millions of years, one pass becomes two, two become four. Eventually, the galaxies may collapse inward anyway, but the path is curved, delayed, unpredictable. Not the clean, cinematic smash that older simulations offered. Proper motion is a quiet saboteur. It does not scream its importance. It whispers, a fraction of a degree here, a handful of kilometers per second there, yet its consequences ripple across billions of years. The cosmos reminds us that certainty is temporary. What we believed was destiny may be nothing more than an estimate built atop incomplete data. Andromeda is still coming, just not in the way we once imagined. New models show that a direct collision within the next 5 billion years has less than a 2% probability. The galaxies may not smash together at all. Instead, their halos could brush, their orbits could curve, and they may pass each other like two ships whose wakes reshape the ocean for ages. Gravity is still the conductor, but the symphony no longer follows a single score. To understand why this matters, imagine two enormous fields of influence, not two pinwheels made of stars. Galaxies are not solid objects. They are networks of billions of stars wrapped in halos of dark matter. Those halos reach far beyond the visible disks, hundreds of thousands of light-years outward. They are not empty spheres. They are the gravitational skeletons that give galaxies shape. When halos overlap, galaxies interact long before their stars ever come close. They feel each other the way magnets feel across a gap, tugging without ever touching. This interaction produces tidal forces, not tides like oceans on Earth, but cosmic tides, differential gravity. The far side of a galaxy is pulled slightly less than the near side. Stars and gas clouds respond to that imbalance. They stretch outward like strands of pulled candy. Spiral arms warp. Stellar orbits tilt. Over millions of years, these distortions become permanent scars, tidal streams, warps, and bridges connecting once separate systems. Even a clean flyby can leave behind structures that last billions of years. The halos themselves exchange energy. When two large galaxies pass by, each moves through the other's dark matter the way a ship cuts through water. The mass behind it lags, forming a gravitational wake. This process is called dynamical friction. It slows the galaxies down, steals orbital momentum, and makes their trajectories less graceful. Even if the first encounter is a miss, the drag created by halo-halo interaction can draw them back for another pass. The universe prefers slow capture to violent collision. Gas clouds behave differently still. Stars are essentially collisionless. They pass through each other like ghosts. Gas cannot. When spiral arms brush, clouds compress. That compression ignites the most dramatic response possible. Starburst events. Vast regions flare into newborn suns, sometimes thousands of them per year. In the Andromeda galaxies, an example here in our universe, this process turned entire arms into blazing nurseries. If the Milky Way and Andromeda pass close enough, they could experience the same ignition, even without merging. Some stars would be stolen. During a near miss, regions at the edges of both galaxies, places where gravity is weakest, are vulnerable. Those stars can be peeled away, forming long, luminous trails that wrap the interacting pair. They do not explode. They simply drift, reshaped by gravity into looping ribbons that orbit the system's center of mass. From afar, it would look like a painter dragged a brush across the sky. These transformations do not require impact. Think of two dancers moving past each other on a stage, not touching hands, yet shifting posture and momentum in response to the other's presence. A bypass on a galactic scale does the same thing. Disk orientation changes. Spin axes tilt. Halo cores sink closer together. Future orbits curve in ways no human intuition can predict. This is why the debate exists. Collision is not the only way galaxies change one another. Contact is not required. Influence is enough. The universe is not a billiards game where objects must strike to interact. It is closer to fluid dynamics, vortices, wakes, perturbations, patterns forming and fading without ever producing a single, definitive crash. So the question is no longer, will the galaxies collide? It has become richer. What happens to two giants when gravity forces them to share the same room? The answer may be far quieter than we once imagined, and far more profound. Andromeda's dark matter halo and the Milky Ways are already touching. Their stars are far apart, but their invisible envelopes have begun to mingle. It is the first contact of two giants, not through light, not through heat, but through gravity. There is no sound, no flash, no collision, just two massive ghosts brushing across 2.5 million light-years of night. Dark matter is the stage on which the future is decided. The halos are not smooth spheres. They are turbulent, knotted, riddled with substructure. Think of them not as clouds, but as weather systems, swirling patterns of gravity, filaments, clumps, and faint streams of mass left behind by every galaxy Andromeda has swallowed. The Milky Way carries a similar history. Each halo is an archive of ancient conquests, stitched together through billions of years. When these archives overlap, gravitational histories collide. Unlike stars, dark matter does not radiate or burn. It interacts almost exclusively through gravity. This means the halos pass through each other silently, particle brushing, particle, barely noticing the encounter. But their gravitational fields do not ignore one another. They twist and roll, curling like ocean currents colliding beneath the surface. The densest regions begin to pull at one another, nudging the galaxies from a distance far greater than the reach of light. In simulations, this phase of interaction looks like the moment before a storm. The cores of the halos remain calm, but the outer layers distort. They stretch toward each other, forming elongated bridges of mass that do not glow, do not reflect, but exert influence like invisible arms. These bridges are gravitational ropes. They slow the motion of both galaxies, bleeding orbital energy into the halos themselves. This process is dynamical friction, but it operates here at a scale no laboratory could reproduce. Each galaxy leaves behind a wake of disturbed dark matter, a region of slightly higher density, like a swimmer pushing waves across a pool. The other galaxy feels that wake. Gravity pulls it backward, slowing it, drawing it in. Not because anything hits anything, but because motion through a sea of mass always leaves ripples behind. Even without a direct collision, this friction changes destiny. A clean flyby becomes less clean. A wide arc tightens. An orbit shrinks. Two giants that might have drifted past each other are coaxed into another encounter. 10 million years later, then another after that, and another still. Galaxies rarely slam together all at once. They spiral inward, the way moons fall toward planets, slowly, reluctantly, always losing just enough energy to keep the dance going. Inside the halos, the smallest companions feel the conflict first. The Milky Way's dwarf galaxies, fragile systems like Draco and Ursa Minor, We'll sense Andromeda before we do. Their gravitational wells are shallow, their stars loosely held. A tug from a foreign halo can tear them apart, peeling them like petals. The same will happen to Andromeda's satellites. They will shed stars into intergalactic space, forming pale tendrils that arc between the two galaxies like bridges of bone. The war begins at the edges. This confrontation does not produce explosions or shocks. It produces outcomes. Subtle shifts in orbits, slow distortions in structure, the thinning and thickening of halos. On human timescales, nothing happens. On galactic timescales, everything does. The halos absorb momentum, exchange angular energy, and reshape the sky. When we picture galactic collisions, we imagine stars smashing into stars. But the real battle begins long before the first starlight ever meets another. It begins in the hush of invisible matter, where gravity sculpts futures we cannot see. The halos are now in contact. The war has already started, quietly, delicately, without the slightest hint that anything is happening at all. Direct star-on-star collisions are unlikely. Space is simply too big. But the gravitational chaos around us could fling the sun outward or pull it inward. Our sky would fill with unfamiliar constellations. We would no longer orbit within a calm spiral arm. We would drift in the turbulent oceans of a new galactic shape. Galactic encounters are not about dramatic firestorms or stars crashing into stars like billiard balls. They are about gravity rewriting the map. When Andromeda approaches, the Milky Way changes shape. Its arms distort, its halo flexes, and its stars, ours included, shift onto new paths. The Sun and its planets become passengers in a massive gravitational reshuffling, drifting not with intention, but with inertia. Right now, our solar system sits in a relatively quiet region, a gap between spiral arms, not too crowded with nearby stars. It is like living in a calm neighborhood between two larger cities. During a galactic encounter, that peace ends. As tidal forces spread through the Milky Way's disk, stars around us accelerate, decelerate, and migrate. The Sun follows the new gravitational gradient, like a leaf caught in a slow-moving current. This migration could pull us inward toward the galactic core, or fling us outward into the halo. Both outcomes are possible. If drawn inward, we would move toward denser star fields, regions where stellar neighbors are closer and the background sky glows more intensely. Constellations would be unrecognizable. Our familiar patterns, Orion, Scorpius, Ursa Major, would dissolve, replaced by mosaics of distant suns and blue clusters born from shock-compressed gas. If pushed outward, we would drift into the outskirts like a ship leaving harbor for open sea. The sky would grow emptier, stars would thin out. The Milky Way's dusty band across the night would stretch and warp, no longer a gentle arc but a knot of distorted light trailing behind. The Sun would become a lonely traveler orbiting the swollen remnant of two merged galaxies. The solar system itself would remain intact. Planetary orbits are tight, gravitationally bound by the Sun's mass, not by the galaxies. Jupiter will not suddenly detach. Earth will not be torn away. But the wider environment, everything beyond the Oort cloud, could change dramatically. The outermost vapor of icy bodies, thousands of times farther than Pluto, is only loosely held. A nearby passing star during the encounter could scatter those distant objects like dandelion seeds, slinging comets inward or ejecting them into intergalactic space. There is another subtle risk: passing stars. When two galaxies intermingle, populations of stars interweave. The chance that another star approaches within a few light years of the Sun increases, not collision close, but close enough that its gravity rattles our long-range debris. A star passing within 1 trillion kilometers, nothing on galactic scales, could yank the orbits of distant comets or alter the trajectories of icy moons. Earth would not notice, but the Oort cloud would remember. Long after the first pass, the galaxies might loop back for another. Each encounter tugs a little more energy from their orbits. The solar system's journey could therefore span billions of years. Gradual drifts, gentle accelerations, small perturbations accumulating like erosion on a coastline. Our descendants, wherever they may be, would inherit a sky that slowly evolves, a horizon never quite settling. The most dramatic possibility is that the sun becomes unbound entirely, not violently thrown into space, but lost in the complicated ballet of orbits. A long gravitational exchange could turn the sun into a rogue, adrift between galaxies, carrying its planets into darkness, where no spiral arms glow, only the faint shimmer of cosmic background light. Yes, impossible? No. The irony is that humans today look at Andromeda and see a serene smudge, a calm neighbor, a distant spiral. Yet its gravity is already reaching across millions of light years, tugging the Milky Way toward a future where our solar system loses its familiar celestial address. We are passengers in a vessel without anchor, destined to sail through whatever shape the cosmos gives the galaxy we call home. If humanity survives into that epoch, it will witness a night sky no one alive today could imagine. The spirals of two galaxies stretching above the horizon, tidal streams coiling like smoke, clusters tumbling through space. The question will not be whether we collide, but whether we learn to endure. Human civilization has been shaped by stable cycles. Seasons, years, the slow tempo of celestial mechanics. The Milky Way has barely changed in human time. We evolved under Orion and Cassiopeia. We farmed under the Pleiades. We launched spacecraft beneath the same constellations painted onto cave walls. Galactic evolution, by contrast, moves on scales so vast that no written culture, no empire, no nation has ever witnessed it. An Andromeda encounter would break that streak. It would turn the heavens into a theatre of motion. At first, the changes would be subtle. Astronomers would notice distortions long before the average person did. Perhaps a dense stream of stars would appear in deep exposures only, an arc forming where none existed before. Later, the naked eye might catch a faint new smudge in the north, a growing brightness in the direction of Andromeda. The galaxy would swell year by year, not perceptibly in a lifetime, but relentlessly over generations. A sky that seemed eternal would betray its motion. Civilizations would respond in ways we cannot predict. For some cultures, the cosmic dance might become spiritual, woven into myth or religion. For others, it would be mathematical, simulations, models, precautionary engineering. Whatever our philosophies, the psychological shift would be immense. Humanity would know, viscerally, that its home galaxy was no longer static. We would inhabit a cosmos undergoing surgery. The solar system itself would remain resilient, but not untouched. Over tens or hundreds of millions of years, the sun's migration through distorted gravitational fields could bring new stellar neighbors. Some would glow brighter than Sirius. Others would emit piercing ultraviolet radiation. A nearby supernova could sterilize planets or strip atmospheres. We might need to develop shielding technologies not for war, but for stars. If humanity became interstellar by then, if we scattered colonies across thousands of systems, our perception would change again. The encounter would not be a single event for a single species. It would be a shared reality of descendants spread across the spiral. Humanity might watch Andromeda's tendrils from multiple suns across light years of separation, each community seeing a different facet of the interaction. Galactic futures would become local. The shape of our galaxy would warp. Spiral arms could stretch like pulled fabric. Regions of star formation might flare to life, blasting newborn stars into brilliant clusters. Those clusters would glow for millions of years, then fade into quiet populations of older suns. If we endure long enough, humans, or whatever we become, might inhabit those newborn star systems, living on worlds created by the encounter itself. We would be children of two galaxies. But the opposite is also possible. Civilization may not survive. The galaxies will merge or miss or loop, regardless of our fate. The stars are indifferent. They do not know we exist. They orbit because gravity guides them. Our presence is a brief accident on the timeline. If humanity disappears before the great encounter unfolds, the sky will still change. Earth will still drift through stretched constellations. The auroras might still flicker over empty oceans. The universe continues. Whether we witness it or not, this is the sobering beauty of civilizational time. Galaxies move on billions of years, species live on millions, cultures on thousands. Even our greatest monuments crumble in centuries. The Andromeda interaction lives in a different register, too slow to fear, too vast to prevent, too magnificent to ignore. We are small, but not powerless. We may not control the cosmos, but we can choose how we meet it, blind, terrified, or curious. The encounter is not a single moment. It is a canvas, stretched across epochs. And if humanity is there to see it, our descendants will not only watch the unfolding story, they will live inside it. Galaxies move not because they choose to, but because gravity demands it. Their trajectories are shaped by mass, dark halos, satellite clouds, and the cosmic web itself. Andromeda does not hunt us. It responds to the geometry of space-time, pulled by the same forces that tug at our own stars. Nothing in the universe is motionless. On Earth, we have the illusion of stillness because friction slows everything down. A car stops without fuel. A ball rolls to a halt. Galaxies, however, exist in a realm without brakes. There is no cosmic asphalt grinding on their wheels. There is no atmosphere to stop them. They move because ancient motions became inertia, and inertia never forgets. Every galaxy is a fossil of momentum from the dawn of time. The earliest matter in the universe ignited in turbulence. When gravity clumped hydrogen and dark matter together, those clumps spun. As they grew into protogalaxies, they inherited angular momentum, the way rivers inherit the shape of the land. Each merger twisted their rotation. Each collision reshaped their path. And so the galaxy that became Andromeda now glides through space with the momentum of billions of past events, none of which we witnessed, but all of which left fingerprints on its orbit. Gravity, too, refuses to leave galaxies in peace. It stretches across unimaginable distances. It drags at every star, every dust cloud, every dark matter particle. Andromeda's forward motion is counterbalanced by the tug of neighboring galaxies, the pull of the Milky Way, the influence of the Triangulum galaxy, and the subtle gravitational web threading the local group. Each force acts like a string attached to a drifting balloon. No string is strong on its own, but together they guide its movement. The cosmic web plays the largest role of all. Galaxies do not float randomly in a featureless void. They lie along filaments, enormous strands of dark matter connecting clusters and superclusters like neural pathways. These filaments are not corridors of light, but corridors of gravity. They direct how galaxies migrate. Andromeda's path is not a decision, it is the slope of the valley in which it sits. The Milky Way travels along the same valley floor, sliding toward the same gravitational basin. Two raindrops do not collide because they choose to. They collide because the terrain funnels them together. Even satellites shape that journey. The Large Magellanic Cloud orbits the Milky Way like a stubborn moon, dragging on our halo, pulling material in its wake. Andromeda's companions do the same. Each dwarf galaxy is a pocket of mass that tugs, nudges, and disturbs the larger system. Think of a meteor passing close to a planet. Its orbit is bent, slightly altered. Now multiply that by dozens of small galaxies acting on two giants over billions of years. The cumulative effect is enormous. Then there are mergers. Past, not future. A galaxy that once collided head-on with Andromeda did not merely disappear. Its momentum lives on, absorbed into Andromeda's mass, pushing it in new directions. If the Milky Way ate a dwarf centuries ago, the stars it absorbed still orbit a little differently, carrying a whisper of the old galaxy's motion. Every past collision is a vector in today's path. None of this motion is linear. When two galaxies approach, they loop and spiral. They overshoot. They lose energy to halo friction and swing back. They are dancers, not bullets. Time stretches the choreography into millions of years, but the physics is the same. Arcs, not arrows. This is why the universe feels restless. Every object is shaped by every other object, even those separated by enormous distances. Gravity is democratic. It does not care if a particle is a star or a speck of unseen matter. It pulls all of them. And when 1,000,000,000,000 stars feel the same pull, they move together. Andromeda is not hunting us. It is falling the way a leaf falls, guided by wind, currents, and the deep geometry of space-time. The Milky Way falls too, and in that shared descent, the future of both galaxies is written not by intention, but by the simple truth that nothing in the cosmos ever stands still. As the galaxies draw near, their halos stretch toward each other. They may already touch in ways our eyes cannot detect. When those halos overlap, forces ripple through the galaxies, subtle at first, then profound. Stars will feel pulls from two centers at once. The dance begins long before the spirals ever meet. Dark matter halos are not decorative halos of light. They are vast gravitational structures, spherical envelopes of mass that extend far beyond the visible disks. The stars and gas that form the glowing shape of a galaxy sit deep inside them. For the Milky Way and Andromeda, these halos are their true size, hundreds of thousands of light years across. When people imagine a galactic collision, they focus on spiral arms. In reality, the arms will meet last. The halos meet first. As the distance between the galaxies decreases, the outskirts of these halos enter each other's range. Astronomers call this phase halo overlap. No sparks fly, and no light is produced. Instead, gravitational fields begin interacting. In the outer region of the Milky Way, a star that once orbited under a single gravitational gradient will begin to feel a second one, the pull from Andromeda's halo. The change is small at first, less a tug, more a quiet imbalance. But on galactic timescales, those imbalances accumulate. This overlapping region acts like a shared gravitational corridor. It does not behave like open space. It has structure, shaped by mass concentrations, tidal forces, and the relative movement of the two halos. Some stars experience increased orbital energy. Others lose it. These shifts do not eject them at once. They adjust their trajectories slowly, altering orbital paths the way long-term erosion shapes coastlines. Satellite galaxies will react sooner than large galaxies. The Milky Way's smallest companions, systems with shallow gravitational wells and limited mass, are especially vulnerable. When another halo enters their environment, it can distort their orbits or even strip stars away from them. This is not speculative. Observations of galaxy clusters show dwarfs being peeled apart when they move through larger halos. Their stars form streams that arc behind them, leaving long trails of their past orbit. Gas is even more sensitive. In the outer halo, gas clouds are diffuse and easily displaced. Overlay two gravitational fields, and the gas begins to migrate toward regions of slightly higher density. It collects in pockets where both halos exert force, forming stable gravitational traps. Over millions of years, these pockets increase local gas density and can become the sites of future star formation. The galaxies will begin generating new stars before their disks meet, not after. Another mechanism emerges when two halos move through one another: dynamical friction. As Andromeda travels through the Milky Way's halo, it creates a trailing overdensity behind it, a gravitational wake. The wake acts as resistance, slowing the galaxy's forward motion. The Milky Way produces a similar effect on Andromeda. This transfer of momentum is gradual, measured not in years but in millions of years. The key outcome is orbital decay. The galaxies become more likely to return to each other after a near pass. The invisible bridge between the halos does not guarantee merging, but it eliminates isolation. The galaxies stop behaving like independent systems and begin behaving like components of the same gravitational environment. Even if the disks never collide directly, the halos ensure they interact. They exchange energy. They reshape the orbits of stars. They influence the paths of satellites. The encounter begins here, where darkness outweighs light. Halo overlap is the first phase of the Milky Way-Andromeda interaction. It is quiet, stable, and almost undetectable. Yet it is the stage that determines what follows. The spirals and bright cores will react later. The unseen structures are the ones that set the rules. Even without direct collision, close passes compress gas clouds. That pressure triggers waves of star formation, millions of new suns igniting in bursts of ultraviolet fire. Galaxies do not simply merge or miss. They sculpt each other, leaving trails of newborn stars that trace their paths like cosmic graffiti. In a normal galaxy, star formation is slow and regulated. Gas moves along spiral arms, accumulating into dense regions where gravity gradually overcomes internal pressure. The process is steady, predictable, and measured over millions of years. But when one galaxy passes near another, the balance shifts. The gravitational fields of both systems distort gas lanes, bend orbits, and exert tidal compression. The physics does not require impact. It requires pressure, and pressure is produced by changing gravitational gradients. During a close encounter, the outer gas layers respond first. They are loosely bound and distributed across long filaments. When those filaments are stretched or squeezed, gas clouds begin to collapse. Regions that might have remained dormant for billions of years receive the equivalent of a mechanical shove. They cross the density threshold needed to initiate star formation. Localized clusters emerge, not one at a time, but thousands of potential sites across vast distances. These events are measured, not imagined. Astronomers refer to them as enhanced star formation episodes or interaction-driven starbursts. They have observed them in systems across the universe. The antennae, ARP 299, the mice galaxies, and many others. Their stellar nurseries glow in ultraviolet because the most massive newborn stars burn hot and short. They flood their surroundings with radiation, ionizing nearby gas clouds and revealing where the bursts occurred. The mechanism behind compression is straightforward. Gas moves within gravitational contours. When the contour changes rapidly, the gas has inertia and cannot instantly redistribute. It piles up. Imagine sand sliding into a trench. It gathers where resistance is highest. In galaxies, the trench is a gravity well created by both interacting masses. Once enough gas accumulates, gravity within the cloud takes over, collapsing it into protostars. Central regions often experience the most dramatic transformation. Interactions push gas inward, toward galactic cores where gravitational forces are strongest. This produces intense starburst phases near the center, sometimes forming tens of millions of stars in a relatively short period. These periods can last tens of millions of years, long in human terms, brief in galactic terms. When they end, the affected region may be depleted of usable gas for future generations of stars. Starburst events also trigger feedback. A massive star forms, then lives fast. Within a few million years, it explodes as a supernova. Its shockwave compresses nearby gas, possibly creating more stars. At the same time, the explosion injects heavy elements into the environment, enriching the interstellar medium. This feedback cycle can accelerate and then shut down star formation. Too much heat and energy can disperse the remaining gas, halting further collapse. None of this is symmetrical. When Andromeda and the Milky Way pass one another, the areas experiencing compression will depend on relative angles, velocities, and gas distribution. A slight difference in trajectory can mean one galaxy generates more stars than the other. Some regions may remain quiet, others may produce newly formed clusters that survive for billions of years. These clusters become fossil evidence of the encounter, long after spiral arms distort and halos merge. The outcome is not uniform. Some new stars remain in the galaxy that formed them. Others end up in tidal streams or bridges between galaxies. They trace the path of the encounter in physical space, forming luminous trails. Astronomers studying distant systems use these trails to reconstruct gravitational histories. If future observers examine our galaxies long after the interaction, the arcs of young stars will tell them how the first pass unfolded. In an encounter between giants, the triggering of starbirth is not a side effect. It is one of the primary mechanisms by which galaxies respond. Before anything merges or collides, their gas is reshaped, and from that reshaping comes light. New suns, new clusters, and new stellar populations, marking the places where gravity compressed matter beyond its limit. Modern observatories do not merely photograph Andromeda, they measure the motion of thousands of stars, detect invisible halos, and map the faintest tidal structures. When astronomers track its proper motion, they see the ghost of its future orbit. Every measurement is a clue in a puzzle spanning billions of years. A telescope does not look into space. It looks into time. Light from Andromeda began its journey toward us before modern humans existed. It crossed 2.5 million light-years to reach the detectors on Earth. When our instruments observe the galaxy, they do not capture it as it is today. They capture it as it was when early hominins first walked the plains. Every photon is a historical artifact that stores information about the state of a star, its temperature, its velocity, and its chemical composition. Astronomers translate that information into models of the galaxy's past and projections of its future. The most powerful tools available now are not the massive mirrors of the past. They are arrays of sensors that measure motion with microscopic precision. Gaia, the European Space Agency's astrometric mission, watches individual stars in the Milky Way and tracks how they move from one year to the next. A shift of a few micro-arcseconds is enough to reveal the direction of a star's orbit. To a visual observer, the star appears fixed. To a precision instrument, it is drifting across the sky like a slow-moving particle in fluid. Multiply that measurement by millions of stars, and you have a map of galactic motion, not a photograph. Andromeda cannot be mapped star by star in the same way we map the Milky Way, but Gaia can track the motion of stars in its outskirts. It identifies average directions, orbital vectors, and the way the galaxy's halo moves relative to ours. That motion is not random. It is governed by total mass, distribution of dark matter, and interactions with satellite galaxies. When astronomers combine these measurements with velocity derived from spectral shifts, the compression or stretching of light waves, they reconstruct Andromeda's trajectory through space. Other observatories supply different layers of data. Radio telescopes detect neutral hydrogen, the cold fuel for future stars. Hydrogen outlines the large-scale structure of Andromeda's disk and the bridges of gas between galaxies. Infrared surveys cut through dust to reveal cooler stars and regions of ongoing star formation. X-ray observatories observe the halos, detecting hot gas trapped by dark matter. No single wavelength tells the full story. Together, they construct a three-dimensional motion model extending across millions of years. Simulations then take over. They do not guess the future, they calculate it. Astronomers input mass, orbital velocity, halo density, and historical merger data. The model iterates the forces acting on every component, stars, gas clouds, satellite galaxies, and produces thousands of possible futures. Most scenarios do not predict a direct collision on the first pass. Instead, they show elongated orbits, tidal distortions, and repeated interactions. These projections are not fixed. As new measurements refine the motion of Andromeda or the Milky Way, the simulation adjusts. Even uncertainty is informative. When a model diverges, astronomers learn which parameters matter most. A small change in halo mass can turn a near miss into a merger. A slight revision in tangential motion can delay interaction by 1 billion years. Telescopes feed constraints into the problem, narrowing possibilities. They do not deliver a prophecy. They deliver boundary conditions within which the universe must operate. These tools continue to improve. Future instruments will detect smaller shifts in position and velocity. They will reveal more stars in the intergalactic medium, map tidal structures we can barely see today, and measure changes in halo shape. With enough precision, humanity will not simply predict Andromeda's path. It will observe its approach in real time, decade by decade. As the future of two galaxies comes into clearer focus through the lenses pointed toward the dark, every statistic about Andromeda is an attack on intuition. 1 trillion stars, 2 million years of photon travel. Halos hundreds of thousands of light years wide. We evolved to judge footsteps and campfires, not to grasp structures larger than entire civilizations could traverse. Human perception is adapted for survival on Earth. Our ancestors needed to track moving animals, recall trails, and identify threats nearby. The distances they faced were measured in meters, then kilometers. Even in modern times, the largest structures we build, cities, nations, fit within a single world. When we hear numbers like 1 trillion stars, our brains attempt to compress them into familiar categories. They fail immediately. There is no equivalent in nature or culture. A single star is an enormous nuclear reactor. The Sun alone contains 99.86% of all the mass in the solar system. It produces more energy per second than humans have ever generated in history. Multiply that by 1 trillion and place those stars in a rotating disk more than 220,000 light-years across. That is Andromeda. Yet when you look at it through a telescope, it appears as a gentle smear of light. The contrast between its simplicity in the eyepiece and its true scale is not a trick. It is a limitation of human cognition. Light years are equally difficult to grasp. 1 light year is roughly 9.5 trillion kilometers. A beam of light travels at 300,000 kilometers per second, and it still needs 2.5 million years to cross the gulf between Andromeda and Earth. Humanity recorded its first cave drawings only 30,000 years ago. Agriculture is 10,000 years old. Modern science is a few centuries old. The light your eyes receive tonight began traveling before our species understood fire. The halo is another failure point for intuition. Most depictions of galaxies focus on the bright disk, the arms, the core, the glowing dust lanes. The true mass lies outside, in a nearly invisible sphere of dark matter extending far beyond the visible structure. Andromeda's halo may stretch to 600,000 light-years. It is so large that if the Milky Way and Andromeda touch halos, their visible stars would still be separated by a galaxy's width. The human mind expects boundaries. Galaxies refuse to provide them. Even the concept of near becomes distorted. The Milky Way and Andromeda are the closest large spirals in our local group. Yet the distance between them is so great that the fastest spacecraft humanity has ever launched would need tens of billions of years to reach Andromeda. That is longer than the age of the universe. We call them close because everything else is farther. Time also becomes abstract. Galaxy evolution is measured in tens of millions or hundreds of millions of years. The formation of a single star cluster from compressed gas might span a timescale equal to the entire existence of the human species. When astronomers say Andromeda will approach us over 4 or 5 billion years, the number is not rhetorical. It is a literal description of dynamical evolution. We do not experience time at that scale. We estimate it, model it, and then describe it using analogies, because no nervous system built for terrestrial survival can simulate it emotionally. The scale of Andromeda does not simply challenge our senses, it forces us to confront the limits of our intuition. Our brains evolved in environments where distance, time, and mass were bounded. Galaxies occupy a domain where none of those boundaries apply. Every measurement we make forces us to build tools, telescopes, simulations, mathematics. We cannot feel 1 trillion stars, we can only calculate them. This is why astronomy becomes humbling instead of familiar. The universe does not shrink itself to human comfort. It is our understanding that must expand. We are not the center of anything. We are a single star system orbiting a single arm of a single galaxy, drifting toward another that may never truly collide with us. And yet, through light and gravity and patience, we can still trace the future of both. The greatest mysteries of the universe are not explosions, but possibilities. Understanding Andromeda forces humanity to confront its scale. Our minds evolved to judge movement across fields, rivers, and mountains, not millions of light years. The Sun feels enormous to us, yet it is a mid-sized star in a galaxy of hundreds of billions. Andromeda holds more than 1 trillion. The solar system is not a special configuration. It is one outcome among countless others formed by rotation and gas collapse inside a spiral arm. When astronomers discovered that Andromeda was not a nebula within the Milky Way, but an entirely separate galaxy, the idea of center dissolved. There was no privileged location, only observers spread across vast distances, each contained within a system too large to experience directly. This realization reshaped astronomy. The universe expanded from one island of stars to a sea of them. That change in perspective is one of the most significant shifts in scientific history. Andromeda teaches a second lesson. The universe does not behave according to human expectations. We prefer clear outcomes, like two galaxies colliding dramatically or avoiding each other completely. The reality is complex. Two spiral galaxies can pass, distort one another, exchange momentum, and then return millions of years later. Their interaction is not a single event, it is a process governed by mass and time. Observations and simulations replace simple narratives. Our species stands at a temporary vantage point. We lived during the quiet era before the encounter. Andromeda is still 2 million light-years away, moving slowly across our sky. Its stars remain distinct from ours, its halo only lightly interacts with our own. Only now do we see it clearly enough to predict what is coming. That timing is not cosmic privilege, it is coincidence, and coincidence is enough. We also learn humility from uncertainty. Predictions about the future of the Milky Way Andromeda system changed when instruments improved. For decades, scientists assumed a direct collision. Gaia's measurements showed otherwise. A small, sideways drift changed probabilities dramatically. That discovery was not a failure. It was progress. Science does not survive by defending a conclusion. It survives by correcting one. Andromeda reminds us that systems evolve without our involvement. Stars migrate. Gas redistributes. Halos absorb momentum and shape trajectories. The universe does not wait for observers, yet observation matters. Without it, the cosmic interaction would occur silently, unrecorded. The ability to measure, predict, and model is what defines our role. We are not powerful on galactic scales, we are capable of understanding them. This perspective influences how we imagine our future. If humanity survives long enough, our descendants will see a new sky. If we do not, the encounter will still occur. The universe is indifferent to our presence, but not inaccessible to our study. That distinction is essential. It is the difference between being insignificant and being curious. Andromeda is a lesson in proportion. It shows that meaning does not require centrality. A civilization existing on a single planet can still detect the motion of a galaxy 2 million light-years away, calculate its trajectory, and understand the forces shaping it. We are small in mass and influence, but large in comprehension. We cannot move galaxies, yet we can map their future. In a universe measured in billions of years, that ability is a kind of existence all its own. As our journey through Andromeda draws to a close, return once more to the darkness between the galaxies. Only slow motion, measured in millions of years, where gravity guides stars and clusters across an invisible landscape. Everything you have heard tonight, dark halos, tidal bridges, newborn stars, and ancient light, exists whether we witness it or not. Yet your awareness of it gives it meaning. We live on a single planet, orbiting an ordinary star. Our galaxy is one of many, and Andromeda is only a neighbor among further neighbors. The universe does not revolve around us. It does not pause for our civilizations or change course for us. And still, we find patterns in distant halos and structure in faint streams of stars. With instruments and persistence, we can measure the future of two galaxies separated by millions of light-years. That quiet skill is its own form of significance. If humanity never survives long enough to see Andromeda expand in the sky, the prediction remains. It will unfold with or without us. Our role is not to bend cosmic history, but to understand it, to look outward and witness scale without fear. To recognize that the motions of galaxies are slow and impartial, and that our place within them is brief but real. Let the vastness be a comfort. The chaos we worry over on Earth is momentary. The patterns we struggle to see are tiny compared to the arcs traced by stars. The universe is not fragile. It has endured collisions, births, and endings for billions of years. It will continue to evolve long after our histories fade. Let your thoughts drift outward into the calm of the night sky and rest. Good night.